Hello. Watch this video if you want a good introduction to logic. And I mean like, you know, what I like to call logic in air quotes. This is my little mascot guy. If this is my first video you've ever seen on this channel, I like to keep him in the top left while I'm working on stuff in what I call meta charts. This is a meta chart. It's a digital like workspace in Paint 3D, because I like Paint 3D, where I make my graphs. Currently, I am making graphs of Principia Mathematica by Alfred North Whitehead and Bertrand Russell, which is a stupendously large work of formal logic. It is a source text of logic for a lot of modern logic. My graphing project is sort of a result of my own needs in terms of learning and retaining what I've learned from Principia Mathematica. But also will, like all of my graphs that I make will be released to the public in albums, so like the 2-star series, 3-star series. Sorry, I'm having kind of digestive issues. They will be released to the public for other people to, use if it will help them. I hope it will help some people read Principia Mathematica. I can't help you with the first 100 pages. It's rough, but if you just keep at it, you can understand it. Now, what we're going over here today, and why this video is special, it's a special edition video, is a complete, I'm not sure what the correct proper term is, but the complete, what I like to call justification for a specific theorem. That theorem is star 326 on page 117 in my edition. I'll leave a link in the description to the edition that I have off of Amazon. It's really good. But yes, this is star 326. The chapters in Principia Mathematica are basically like that. So the 3 denotes it's in the 3rd chapter, and the 26 denotes what theorem it is. The numbering system isn't completely linear. For instance, there is no 6-star, 7-star, or 8-star. It goes straight from 5-star to 9-star, right? Or rather, star 5 to star 9. We can get into that another time. The purpose of this episode, like I said, is to examine 326 because it is a peculiar and honestly perfect specimen to demonstrate this on. Now, we're going to look at how it's written in the book before we get into all of this. Don't worry about this yet. If this looks alien, that's totally fine. This is how it is written in the book using what is called dot notation. Now, we're going to get into that in a minute. What this says here, so I'm going to type it out. So this is the assertion sign. You can think of the assertion sign as the start of a, think of it like a capital letter at the start of a sentence, right? Okay, so that like starts the theorem or expression, whatever you want to call it. There's more to the assertion sign philosophically or what have you, but that's all you really need to know for now. So what this right here would say in what you might call modern, right, is P implies Q implies P, right? I'm not sure if you would like wrap that like this or what. I'm not very good at modern notation. I first learned dot notation reading Principia. Like I first learned formal logic, I should say, learning as I'm going right now through Principia Mathematica. That's another reason why I'm making this, is that this is all fresh in my mind as someone who's like learning through reading this book instead of like, learning the through the normal modern channels. Like, I've tried learning as an autodidact through the modern notation, and modern notation to me is just way too confusing. And the notation, the dot notation in Principia Mathematica ended up being way more easy to understand. So, like, right here, this right here, okay, what that says is not, hold on, not P or, that's the disjunction, we'll cover that in a second, but not P or not Q or P, right? That's what this says right here. Now, we'll cover exactly what that means in a minute, but we need to start, ironically, at the very bottom. Now, these are color-coded for a good reason. The green is the stuff that we're going to be we're going to be following. Think of it like a rope, right? A guide rope that leads you back to the start of a cave. You know, this is going to be the stuff that we're guide roping back to this stuff, the simpler stuff. Now, the first thing that really kind of needs to be pointed out, this is our workspace, by the way, that's why it's a different color, is that this is our active workspace. Now, if you are entirely new, and if that's why you clicked on this video, don't worry about it, right? Like, if you're entirely new to formal logic, like, don't be intimidated. I'm going to explain this as I kind of came to understand it. The first thing to really make clear, and is actually made clear in the first, like, 30 pages, like the first 10 even, of Principia Mathematica, is how, let me look, is how this works. So, say we have, I'm going to make this larger. Say we have P or Q, right? What that means is either P is true or Q is true. Now, actually, I kind of messed that up a bit because the exact wording is just P is true or Q is true. Either would sort of imply a different thing, so ignore that. Right? Now, if I say today is Wednesday or Thursday, right? It doesn't really, like, it doesn't really matter if Wednesday is not the current day of the week, right? The idea being that a better example of how the or works would be like, it is day or night isn't a bad one, but that still implies, like, exclusion. The point is that the statement, it is day or night, like, the simplest version of this is, the statement, it is day or night, is only false if it is neither day nor is it night. Right? As long as one of those is true, the statement is true. Now, the thing is that in a disjunction, both can be true, and it doesn't really matter, right? So in P or Q, P or Q can be true, and it will be true. It doesn't matter if both are true. What matters is if and only if both are not true. Then the statement is false. Right? So while it can't be day and night, right, the statement is true if it is day or it is night. And if it is neither day nor night, then it is a false statement. And the only reason why, contextually, it is day and night can't really be a true statement is more like a metalogical thing. Like, oh, well, you know, it can't both be day and night at once, and yada yada. Like, the point is that the actual disjunction works that way. Now, a logical conjunction is and, meaning it is P and Q, rather than P or Q, which entails that both P and Q, as you might guess, need to be true for the statement to be true. Pretty simple, right? So, like, say you have the statement the bug was red and green. If the bug in question is neither red nor is it green, the statement is false. As in, if it is missing either color, red or green, it is false. This is shown. If you hear that, that's me flipping through my book forward, right, to in 301 as P and Q is identical to not P or not Q. Which makes sense if you consider, oh, and in a more modern format, that is P and Q is identical to not, hold on. I have my handy dandy special character thing, because if you hit any actual, like, if you hit like A, B, like any letters on the keyboard, it messes this up if you're holding Alt. But not P or not Q. Okay? So that's what this is translated into more modern notation. Because this little symbol is used as not in Principia Mathematica. This is the more modern not symbol. These dots, whenever used in between like actual entities rather than as operators, function as conjunctives. So this functions as a conjunctive. We'll get more into that later. But they mean the same thing, right? But anyway, as we were getting into, this makes sense if you consider what the and is here. It means not this or not that. So again, if the bug was red and green, it is not red or not green. What that means is to further dissect that. I'm thinking of how to put this, like, spatially, to, like, spatialize this. So, if you put in here, let's, like, hold on, let me undo that. Let's make the circle out here. Let's make it empty. So, by the way, this is a blank canvas. So, like, you can copy, paste. That's how I do these, right? So, let's turn that into a Venn diagram, right? This will probably be useful as we go into this. Now, you look at red, and then green. And here's the clever twist, right? This is not red. And this is being a little difficult. There we go. Come on. Paint 3D has a mind of its own sometimes. Not green. And this is not red. And not green. Right? I mean, it's pink, but you get the concept, right? Like, this is not green. This is not red. This is not both. Okay? If that's a little mind bending, I get it. But it's that concept. It is both not red and not green. It is not red and not green. Right? It is red and it is green. Right? It's that's a little bit of that might be a little bit mind bendy, but hopefully you get the idea. It is both red and green, so it by the inversion is not red and not green. It is exclusionary. Let me put that back up to exclusionary. The statement, the bug is red and green, is exclusionary to the bug being any colors other than red and green. Meaning, if it is only red, it is not red and green. And if it is only green, it is not red and green. Right? So that's how the conjunctive works. These are the basics, by the way. Like, we're analyzing the basics. Now, in Principia Mathematica, interestingly, the conjunctive is defined as not P or not Q, though, from what I understand, it's shown in Boolean logic that actually Um, not and can be used to make all of the basic logical operators, but we'll get into that, if not in this episode, then way later. So to get to the next Principia Mathematica relevant, like, atomic idea, we get into negation, right? So to look at page, I'm trying to find out where it is. The contradictory function, as it's called on page 6, is simply, right, it's simply negation. So negation is something already kind of covered. It's the concept of not P. Not P, or not P. For every P, there's not. So if you say it is dry, there exists not dry, right? For instance, if you say the car was blue, there exists a not blue for the blue that the car is said to be in. I kind of mangled that sentence. For the blue property that the car is stated to have. Right? We just kind of went over this, but that is a very, 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 whoops, very, very simple idea. It does a lot of work, though. Right? I mean, we all understand what this means, what negation is, what inversion is. You have the apex, you have the nadir, you have the apogee, you have the perigee, you have the hot, you have the cold, you have the light, you have the dark, you have the left, you have the right, you have the up, you have the down, you have the forward, you got the back, you got the X, you got the Y, you got the, you get the gist. You got the red, you got the blue. It's the not, right? And not, by the way, can be finicky, but let's just stick to the abstract concept of negation as presented. No extended philosophical meanderings. So now that we've covered that, the most complicated of the basic ideas here will be implication. But first, let's talk about identity, and specifically what identical means. So I just want to make sure I get it correct, basically exactly as it's presented in the early stages of Principia, because it is very, very important to get this correct. I thought that they covered it rather early. I think they actually cover it way, well, maybe not way later than I thought, but they do cover it later than I thought, I guess. Here we go. On page 23, they cover identity, which is later than I thought. Identity has some basic functions presented. Wow, I mauled that. Presented on page 23. Wow, that typo, huh? That we should cover here. They are reflexive, symmetrical, and transitive. Now, reflexive would be x is identical to x. Simple enough, right? When it holds between itself, I'll just quote directly from the book. A relation is called reflexive when it holds between a term and itself, either universally or whenever it holds between that term and some term. I wasn't looking at the screen while typing that, so yeah. To translate, this basically means what it sounds like. And what it looks like. X is identical to x when x is identical in relation to itself or others. Right? Now, what symmetrical means, right? X, it's written in the book as x is identical to y is equivalent. Where is it? Here it is. Is equivalent when y is identical, or rather is equivalent to y is identical to x. Okay? Just trying to figure out how I'm going to handle that, because, you know, folder popping up. But anyway, I think I'll just keep that in and just blur it or something. But here. X is identical to y is equivalent to y is identical to x. To continue from that awkwardness. Which is kind of simple enough, but we will explore equivalence in a bit to make it make more sense. It's described in the book as the second of the above propositions, meaning the proposition shown that x is identical to y is equivalent to y is identical to x. Expresses that identity is a symmetrical relation. A relation is called symmetrical if whenever it holds between x and y, it also holds between y and x. What it sounds like. To give an example, we might say that if watering the grass is helping it grow, then watering the grass is helping the grass grow. Or for another example, trying to think of one, we might say that if x is a waste of time and y is a useless activity, then x and y are identical in that they are both wastes of time, right? And that, or put another way, that x is a useless activity if it is a waste of time, and y is a waste of time if it is a useless activity. Get it? They're the same thing. Now, the transitive concept is that x is identical to y, x is identical to y, and y is identical to z, implies x is identical to z. Is also kind of simple, but let's explain it anyway. In the book, it is said that a relation is called transitive if whenever it holds between x and between y and z, it also holds between, and by the way, there's some commas in there. It also holds between x and z. So if x is identical to y and y is identical to z, then x is identical to z. So if x is a waste of time and y is a useless activity, if y is a useless activity and z is a futile, I was thinking falafel there, if you're wondering where that came from for some reason. I think I'm hungry. I might want to go get something to eat. Is even a futile endeavor, then if y is a waste of time and x is a useless activity, if y is a useless activity, or rather, if y is a futile endeavor and z is a useless activity, then z is a waste of time and x is a kind of getting lost in my own metaphor here, futile endeavor. If one is the same as the other and the other is the same as a third, then they are all identical. Get it? Now, the reason why this is important, identification is important. Just ask your local government. Jokes aside, it's actually very, very important to identify identicalities or whatever, because to understand what being identical is, the property of being identical, is to understand a sort of connective tissue that is very, very important. It is very, incredibly even, difficult to describe in direct language, and you'll sort of understand what I mean very, very, very soon as I explain implication. Okay? We good? That's me clapping. Do you get this? Good? Okay. I'm going to stop recording here, and then I'm going to come back after I get something to eat, because clearly I have food on the brain. Okay. So, I'm back. I didn't get something to eat yet, but hopefully we will have no more falafel-induced spelling errors. We were getting into the concept of implication next. Now, the reason why identity is important and why I went into it before implication, even though implication is covered as a basic thing in the book prior to yeah, prior to identity. Sorry, I'm just reading through. And by the way, the logical product and logical sum are both covered early, but again, the logical sum is given as, to rewrite that, not P or not Q, right? We've already covered that. I'm just explaining that again, that's why I kind of covered them in the way that I did, because you kind of, disjunction explains conjunction in a pretty, I think, cool way, you know? Hear that? That's me getting some tea, like drinking some tea through a straw. Okay, so we've covered the logical product, which is, the logical product is conjunction. The logical sum is disjunction. So let's cover that. Like the names, the fancy names of what we've covered so far. Logical product. Well, let's do them kind of in order, right? Contradictory function. Negation. Not. Or, this. Not. Etc. Now, the logical sum is disjunction. right? I'm not sure if there's a different, I'm not sure if, like, with the contradictory function or with the logical product, which we'll cover next, if there's, like, another alternate one of these, right? Like a little symbol. But if there is, whatever. Logical product. Conjunction. Uh, that's how it looks in dot notation. We'll cover that whenever we get to it. But, that's the conjunction symbol in modern. Right? So we've got the contradictory function, the logical sum, the logical product, and I'm not sure if it's called, like, a function, but identity, right? Okay, and next is the implicative function, or implication. Now, the thing here is, I understand that in Principia Mathematica, what is simply called implication can be a tad bit different from what is called a material implication in modern, or some such. Just understand that for the purposes of this video, whatever, we'll be using just the term implication for what, if I remember correctly, is normally called material implication. So, the implicative function is to put it exactly as it's said in the book, the implicative function is a propositional function with two arguments, p and q, and it's the proposition that either not p or q is true. That is, it is the proposition not p or q. Thus, if p is true, not p is false, and accordingly, the only alternative left by the proposition, the proposition, yes, not p or q, is that q is true. In other words, if p and not p or q are both true, then q is true. In this sense, the proposition not p or q will be quoted as stating that p implies q. Now here's the idea. Oh, also I forgot a quote. mark. Ah. Let's just, look, if you won't tell anybody I forgot that, I won't tell anybody that you noticed. Okay? Alright? We good? Okay. So, if this isn't really making quite sense, like, check it out. So, not P or Q is a proposition. Not a proposition. Meaning, it's sort of a to illustrate what they, Alfred North Whitehead and Bertrand Russell, are talking about here. Consider the statement, it is either not raining or the ground is wet. Right? Now, if it is raining, then the statement's section of not raining is obviously false, and the true statement left is the ground is wet. The problem with this is that implication on a truth table is more like how to put it. Well, not P or Q is a little abstract, because the only way for it to be false is for not P to be false, I think, and Q to be false. So essentially, P is true and Q is false, renders it false. P can be false and Q can be false, and it will still be true. Or P can be false. Well, no. Well, yeah, okay, all right. I got confused because P can be false would be like not P, right? So Q can be if Q is false and you get the idea, right? Like, I'm getting myself confused, so here, let's make this like really, really easy to understand. Because like I said, even I'm getting confused. And I understand this from like a Boolean perspective rather than a propositional logic perspective. So like, check this out. E Q. Let's just put that output, right? So if you have, right, like, yeah, okay. So, true and false. If P, well, if P is false, you've got not P, right? So that's not P. So, reminder that not, oh, hold on. I'm being a bit dim. Sorry, folks. Hold on. Not P is false, right? Or in other words, if P is false, not P. Okay? That's why they say not P or Q. Okay? Like, that's what it is. It's the proposition that either not P or Q is true. That is, it is the proposition not P or Q. Thus, if P is true, not P is false. Right? So if we look at what that means, and we got to get rid of that because, come on. So if not P is false, or rather if P is false, then it's just not P. Here. I'll even add like a little to help us keep track of this, because I'm getting confused too, folks. Right? Then it's true. Because both are true. This is both are true, technically. Not P is true if P is false. Right? And Q is true, so you get true. Alright? So if P is false, again, like, well, I'll just put that there because I needed that anyway, but so if P is false, you've got not P, and if Q is false, you've got a clever trick. Then it's still true. Right? Because what we're, again, evaluating here is not P or Q, which is P implies Q. Right? These are the same thing. These are identical. So remember, this is what we're evaluating. It's not P or Q, aka P implies Q. So, if P is false and Q is false, the proposition is still true. Like, the truth value is still that it's true, right? Because the proposition is not P or Q, right? So, again, if the proposition was something like, it is not raining or the ground is wet, if the ground is not wet and it is not raining, then the statement is still true, right? I use that example because it's very intuitive, but that's not, you shouldn't like look too deeply into that. It's more of a literal, if P is not true, right? If this is the statement, right? You take these as variables, kind of like x in 1 plus x equals 3, right? Like, you know that x is 2. It's the same thing here. Whatever you want to put in for x, like, what's actually being said here is we're talking about the logical assembly here, right? That's kind of what makes this all very mind-bendy. So we'll just keep it in the abstract and only use the example of, like, raining or ground is wet, right, whenever we must. So this right here would be, it is not raining, rather, and the ground is wet. Still true, right? Because not P is true, it is raining, or rather, it is not raining, right? You know what I mean. P is false, meaning not P is true. So, if P is false, meaning that not P is true, and in this case, not P is, it is not raining, right? And the ground is wet, it is still true. And I mean, that could be the case, right? I mean, it could be that it's not raining, but for some reason the ground's wet. Like somebody threw a bucket of water, or the sprinklers are on, or whatever, right? Now, in this instance, not P is true, aka P is false. And we have Q is false. Now, it still comes out as true, that proposition, and this would be the equivalent of, it is not raining and the ground is not wet. Well, that's kind of, in our example, self-explanatory, right? Now, the difference here is that you get into, what if it is raining, but the ground is not wet? Which would be P and not Q, right? And just for completion's sake, let's go ahead and make it clear that up here in this, that this is Q. That Q is true. That Q being true is Q, right? Now, this is where it's false. The proposition is now false because it is not P or Q. So not P or Q is if I'll remind you, if this proposition is to be true, then either P then not P or Q needs to be true, right? Right. Like, just making it clear again that we're evaluating the truth of not P or Q. Okay? Right? Like, to get a grip on that. That's what you're evaluating in this. And I promise this all dovetails into why we're actually here and the rest of this chart. Okay? But this is the very basic stuff if you want to, like, really get into this. Now, this would be, because it is not P or Q, if P is true, right? You can. I'm not doing it properly. Hold on. There we go. That was a good one. Pop that, and then this is gone, right? Because you had not P. If P is true, then right, and if not Q, right, then the reasoning why is because if you think about it, not P is identical to not P. And obviously, Q, excuse me, P is identical to not P, and not Q is identical to not Q, right? Something like that. I'm laughing because it's like, okay, I'm kind of overdoing it a bit. The idea here is that not Q is actually identical to Q is false, right? Sort of, kind of. You get the idea. Like, I'm trying to condense a lot here, but the idea is simple: that if not P is false, then you get P. If Q is false, you get not Q, right? So this is no longer true. Like I said, if P is true, there we go. I don't know why I can't do that today. And if Q is false, well, and you're left with a symbol that doesn't mean anything. Now, then, like, this whole thing just isn't true then. Like, if Q is false and not P is false, which would mean, you know, P, then this is just false. Now, conversely, if both of them are true, well, I mean, you know how disjunction works, right? But that's why P being true makes Q the only option left. Okay? Because it's true if not P is true. It is true if Q... Okay. So again, the thing that's confusing is this. The idea is very simple. And in fact, I cover it up here. This is what it looks like in a graph. P implies Q is identical to not P or Q. Okay? This is how I graph these things. This is what I'm explaining here. This is literally 101, is P implies Q is identical to not P or Q. That's what this is, spatialized. Now, the way I like to look at it is a seesaw. A weighted seesaw. Not P or Q, that is. So what I mean by that is you can look at it like this. Not P is over here. Let me invert that. Q is over here. And not P is over here. Right? Here's my handy dandy visualization. Now the thing is that it becomes flat, right? If P is true. This is how it's like, this is how I kind of like to look at it, is that this is how it looks whenever you have P being true. Right? It's no longer an or, though. It becomes an imply symbol, but you get the idea. Now the idea is that it's fine if the roles are reversed. Right? Yeah. I'm messing this all up. You get the idea, though. I think if not Q, performance anxiety screwing me up. If not Q, okay. And not P. I'm an idiot. I could have just done this. But you get the idea, right? Like, if not P, yeah. And not Q, then it's still okay. right? Now, the only time that you lose is if the right side of this touches down. So if you get, like, again, let's just invert that. If you get P and not Q, it touches down on the right, and, you know, that's the lose condition, if you will. Okay? Like, that's kind of the way that I view it. It's that the seesaw touching down on the right is invalid. That's like my mental model of this, is basically what you're seeing here. That it's okay as long as you don't have the seesaw touchdown on the right, right? If you need a visualization. Again, the idea being that the only way for it to be true, if P is true, is for Q to also be true, because P has basically cut off not P. Alright? I hope that kind of makes sense. I'm mashing undo as quickly as I can. We'll get there. We'll get there, folks. We'll get there. Okay. So that's the basics, right? That's the contradictory function, the logical sum, the logical product. Now, to explain, as far as I've had it explained to me, why they're called the logical sum and the logical product. This is a bit mind-bendy. So in Boolean, how true is 1 and false is 0, same idea. Literally the same idea. 1 plus 0 can still equal 1. 1 times 0 equals 0. Right? Okay, so that's a logical. Okay, so that's like P or Q, right? Well, this is more equivalent, if I'm going to be real. So let's get that's 2261. Okay, good, I can just type that. That's more equivalent to P or Q, and this is also kind of equivalent to P and Q, aka P and Q, right? Because if in P and Q, you have either P or Q be false, you have a false proposition. And in P or Q, either one can be false. Only if both are false is the whole proposition false. So you can think of it as t plus f equals t, t times f equals f. Sum versus product. This has a few implications, to say the least. So P or Q or S or R or R I can't, or S can be true if any three are false, but one is still true, as it's effectively TF plus TF plus TF plus TF equals question marks, right? If one is true, the whole shebang is true. But in P and Q and R and S, if one is false, the whole thing is false, as it is true. TF x TF x TF x TF TF equals, right? Got it? False times anything equals false. True plus false equals true. This makes a lot of sense when you consider, again, what we covered earlier regarding the red and green bug and night or day. Now, non-exclusive OR doesn't care if both are true. True plus true in a non-exclusive OR not the same as not exclusive OR, aka XNOR, operation, proposition, whatever. Right? This is important as XNOR means only one or the other, not the same as OR. Yeah. But in a non-exclusive OR, if both are true, all right, hold on. In a non-exclusive OR, see, I got confused. I literally just wrote don't confuse them, and I got confused. In a non-exclusive OR, aka a regular old OR, aka this, right? Both can be true. But, as just explained, in an exclusive OR, both components or in multiples, if I remember right, it's odd numbers of components or something like that, need to be true, false, whatever. Point is, in this logical disjunction, it doesn't matter if both are true. Whether or not it matters that both are true is a separate concept. Or rather, it mattering that both are true is a different concept. If that's confusing, check out my stuff on Boolean. Okay? And I just cut that off, so I hope you got that. Anyway. Point being is that what we're covering here, as I said, we'll just get rid of all of the confusing stuff. All you really need to remember is this part. Alright? We'll just forget all the other crud. I probably shouldn't even have mentioned it. That's more technical, but like I said, if this is confusing, consult my videos on Boolean. Alright? But that's the idea. At least that's the way I understand it. So far we've covered the basics. Now, you may be wondering, when do we get to the other stuff with the green and blue and purple boxes? All this stuff. Right now. Okay? We're getting there, like right now. Okay? So, understanding this. This is how my graphing system works for graphing Principia Mathematica. It is spatializing. This is a direct one-to-one. This means the exact same thing as this. This is a nesting operator. You don't need to understand what it says, other than that it is different from this. This is the symbol that signifies this group. Okay? This is the symbol that signifies this group. That is all that you need to know. They are literally designed to be alien, that you don't recognize them, that they are a symbol from a language you have not seen, that doesn't clash with Latin, Greek, or Hebrew characters. Any of the characters that you would normally see, let me see, it's Latin, Greek, trying to think of what other characters are used often. But it's basically so that you're not seeing Latin, Greek, or Hebrew in it, that it is literally, or English even, that it is unique, and that it just signifies this is this grouping. And it is also to help you understand that you can look at something and recognize it as that thing without like an associated word. Like, oh, this is blank. This is the symbol for, right? It's to help if you're reading this, right? Because that's how I do it, kinda. Like, that is how my brain works. I have, as you'll see on my, if you go look at my home page, like my home tab on this channel, you'll see a short video about what is Logic-Mysticism. And in that I explain that I have kinesthetic synesthesia. That is something that I do. And this is how I kind of view it, is that I look at it and without needing a word associated with it, I can understand that that is symbol for. Now I know what the symbol actually does mean. I still look at it like, you know, the symbol for group, right? Just because it has a meaning doesn't mean you need to know the meaning. Just understand that that's what it means, basically, right? So this is the implication symbol. This is Q implies P or Q, right? This is P or Q is identical to not Q or P. Now, the reason why I skipped over equivalence, okay, it's kind of simple. And it is because I'm going to show you equivalence right here. If I can find the exact, right. Here we go. So, equivalence is written as, that's the wrong one. Rip. I'm dim. I should know better than that. It is, I'm looking for this one. Yes. Equivalence is written as, let me just go ahead and do this. Okay? To make this astoundingly clear to anybody who's used any kind, like, to regardless of your level of understanding of what dot notation is like, this is like a layered translation of dot notation to modern. Okay, I learned dot notation through Principia Mathematica. I'm not sure if I said this already because I just could not learn modern notation. It was way more confusing to me than dot notation. So if you find a more modern notation style, like with parentheses, to be more natural, then here you go. What I'm about to show you is, like I said, just what it is. So let's get rid of these, right? I should have done this before I added it, because, to save myself a little bit of the configuration process, but we'll deal with it. Here you'll actually see me doing some graphing. Like, this is kind of how I just do this stuff, yeah? So, yeah, I could just take these from here. But I'd rather not. Hold on. I'll take this, though. Just pop that out. Now, the reasoning why I'm not doing it directly on the canvas is because Paint 3D does weird stuff if you do that. Just saying. It's worth it to know that. If you decide to get into this for some strange reason. I know it's not exactly something many people want to quote-unquote get into, but there you go. And maybe just watching me build it piece by piece will help you understand, like, the graphing system a little bit better. So, my ear got itchy, that's that noise if you're hearing it. You want to see a neat trick? I think I showed it off. Well, yeah, I definitely did show it off earlier, but check this out. I don't need to go copy P, or rather Q, because I already have. How cool is that? How's that for an identity function? P backwards is identical to Q forwards. There you go. That's an identity function right there. So yes, hopefully this is intuitive enough for you to get the idea that this is equivalence. That equivalence is just like if P and Q are equivalent, then P implies Q and Q implies P. So you could almost view it as like a circular relationship. It's like not P or Q. I hit Alt there. And not Q or P. Alternatively, again in modern, it'd be like not P. Well, I guess not in modern, but if you wanted it done in dot notation with the modern conjunctive operator, you'd go not P or Q and not Q or P. And if you wanted it in modern, like more modern, not P or Q, not P or Q, not and not Q or P, right? Whoa, whoa, whoa! I'm taking the box, not the. What a spectacular error. So this is basically what you're left with, right? Does that make sense? So The idea being that P is true makes Q true, Q is true makes P true. You dig? You can just, I mean, I know it's a little mind-bendy, because it's, to put it another way, to give even another demonstration. What does tolerance mean? What the heck? Tolerant? Why does a paint bucket have a tolerance? So it's, check this out, right? Check out my super awesome Paint 3D skills, where I totally mess up a template, because I'm dim. Anyway, yeah, let me like get rid of that. Wow, that's just, yeah, that doesn't look good. Hold on. We can do better. I know I can do much better than that. Hold on. There we go. Copy. Paste. P. Uh, not P. Ah, crud. Actually, I should have just left that there, yeah. Uh, this is time to demonstrate something cool. If you copy and paste something in Paint 3D, and then you paste it, it goes in the original spot. How cool is that? What a lifesaver. Anyway. And again, as we've already discussed, P is secretly Q in disguise, and Q is secretly P in disguise. Actually, let's just rotate that. We don't need another one. Boobige. Boobige. No, being true. Now, some persnickety people would take umbrage with the phrase make P true, right? Let me be clear. Make true meaning for the proposition to be true, X must be true, meaning if the proposition is true, then X must be true. So P making Q making not P or make Q true really is just me shortening the phrase P being true renders not P or Q false if Q is false. Therefore, if not P or Q is true and P is true, then Q is true if P is, yeah. Because that's a ton of words and it's just dim when you can get the point across easier and more intuitive with P makes not P or Q make Q true. Okay? For the persnickety people who might go, well, actually, it doesn't make it true. It just means, yeah, I know what it means, okay? Like, I know what it means, you know what it means, you know I know what it means, you know I know that you know that I know what it means. Don't actually, alright? Like, there's no point in that. Stop it. You know what it means, you know what I'm trying to say, you know the message. Don't be persnickety. Anyway, that's equivalency, okay? Now, what Principia Mathematica, and by the way, when I say what Principia Mathematica says, means, by, etc., what I'm saying is what Alfred North Whitehead and Bertrand Russell never remember if BR's last name has 2 or 1 L's mean in PM. Means when it says formal, I believe it's formal equivalence. In the book's own words is now I think they get to it in I think they get to it after they get to it in formal implication. When page 21, formal implication. When an implication, say, I'm going to need Greek letters. I know how terrifying. I need phyrexia and cactus. So there's phyrexia and cactus. I'm keeping those up there for now. And I'm resetting this so that it doesn't... I'm stupid. I'm resetting this so it doesn't cut it off. But, yeah, because now I can't copy that. But I'll just put it right here. Say phi x implies... And you don't need to understand the whole phi x thing. Just understand, much like this, right? Much like this, just read phi x as just this thing that implies another thing, okay? Just for simplicity, just phi x and psi x, just take it as thing implies other thing, okay? We're not going to explain propositional functions and arguments and individuals in this episode. We are just looking at phi x and psi x here as part of a quote from the book. It is not something that you need to worry about. It's just when thing implies thing. When an implication, say, thing 1 implies thing 2, is said to hold always, i.e., when and that's an existential quantifier. Again, you don't have to worry about that. What this means is literally x is always true for phi x implies psi x. But it's not even that. It's, as they say right here, i.e. when x always phi x implies psi x, which again may not make sense, right? You don't have to worry about that. As they explain here, we shall say that because they put it on italics, I'm going to put it in italics here. Well, I guess I can't put it in italics. Well, whatever. We shall say that phi x formally implies psi x. And propositions of the form will be said to state formal implications. In the, yeah, hold on. Anyway, I'm going to make these apostrophes so that it's clear that this is within the greater quote. But anyway, sometime later, two functions phi x psi x are called formally equivalent when each always implies the other. Okay? So that's what you need to know about formal implication and formal equivalence. So formal equivalence is whenever something always implies the other thing. Or, yeah, okay. So formal equivalence is whenever equivalence is always true, right? So like if one thing always implies another, that's a formal implication in Principia Mathematica. When one thing always implies another thing, and that thing in turn always implies the first thing, that's a formal equivalence. Right? So this is just a normal equivalence. A formal equivalence is whenever they always imply each other. Now that seems a little curious, I'll admit, and that makes more sense whenever you understand what phi x and psi x are. This is like the next level up of understanding what we're talking about here, so don't worry about it. Don't worry about it. The thing you need to understand is this, okay? We will at some point have an episode of this that is like a sequel to this episode where we go into what phi x and psi x are. Now, that is all groundwork. We don't deal with equivalence, I don't think, in this episode of, understanding formal logic. But what we are going to do is now start explaining how this stuff works. Okay? All of that was necessary for you to understand what comes next in this episode and every other special episode that is like this one. I am super duper mega ultra serious about that, so be serious in retaining the stuff we've gone over if you want to really understand, absorb this stuff. If there is one thing and one thing only you get from this video, if you enjoy the idea of learning propositional logic, it is this. Read Principia Mathematica. Do not listen to people who tell you not to. They are wrong. Okay? Okay, I cut it off, so let me rewrite that. Seriously read Principia Mathematica. People who tell you it's too old or it's too difficult, whatever, are wrong. If you want to learn logic, read PM. Seriously. It's what I'm doing, and it is great. Okay? If you don't watch another video of mine, and I will probably cut this, clip it, and put it at the very beginning, if you don't watch a single other video that I make, if you don't retain a single other thing that I have to say. If you don't like my little mascot, if you don't like my voice, if you don't like my graphing system, if you think I'm a big dumb doo-doo head, if you think my graphs or whatever are serious doo-doo butter, please just read Principia Mathematica. If you are watching this video, and you are watching this video not because you accidentally clicked on it, but because the title, the idea, intrigued you for whatever reason, even if you already understand formal logic as a professional, academic, and you have not read Principia Mathematica, do it. Do it now. Do it. Seriously. There are very few things I will ever be like this serious about on my channel, whether it be this channel or my gaming channel. Read Principia Mathematica. I am not joking. Read the darn book. Thank you. The mascot approves. Seriously. And of course I'm having nasal issues as I'm trying to be serious, because I am just not a serious person. But I am serious about that. Read the book. Okay? Like, seriously, read it yourself. No, I would even say, especially if you watched this video, especially if you go on to watch other videos I make, or other videos about logic, read the freaking book Principia Mathematica by Alfred North Whitehead and Bertrand Russell. This is not a joke or a bit. I am being super duper serious. Okay? Okay. So one more time. This is equivalence. And more importantly than just like equivalence, because we're not like nothing over here actually deals with equivalence. It's just something important to cover as part of the basics. As importantly, this is like the Rosetta Stone of how, right, this works. This is the graph that corresponds one-to-one to what's above it. Okay? P is equivalent to Q is identical to P implies Q and Q implies P. Okay? If you can read this, you can read the rest of the graphs that I'm going to be covering. Ah, crap! I have to click undo a million times. We'll get there, folks. Okay. Now then, with all of that said, okay? We can finally get into 326 and how this all works, okay? Now, 326 on page 117. You may be wondering, like, wait, if we're doing basics, why are we starting with 326? And it'll make sense in a minute, I promise. So on 117, 326 caught my eye as I was graphing. Now, my progress has been slow lately in graphing because of stuff in real life and because I've been doing stuff with my gaming channel whenever I've had the time, instead of just doing graphing. Goodness, I'm sorry about that, folks. I don't know why my nose is so stopped up. But I got to 326, and normally I just go through these because I understand what this is, and we'll be going into, that's actually what this is all about, is what these are. And how to read the book. I am basically telling you how to read the book. I am basically showing you how to read the book. This is where the lesson, if you want to call it that, I don't want to call it that, starts. We can now officially begin the presentation. That's what I actually call it. That bugs me. We can start the presentation now, okay? So, this is pretty simple. It's P and Q implies P, right? That might seem so simple it beggars belief. Like, what? Right? Now, if you don't understand why P and Q might imply P, we're going to get into that. That's what the rest of this green box stuff is. Okay? So the demonstration, my mouse has a problem. My mouse wheel has a problem where it likes to just do that if I don't press the button to lock it in place. Which is why I like having the mouse that has a lock button on it for the mouse wheel. It also basically turns the mouse, like the middle mouse button, into an actual button instead of an annoying, stupid thing that you can't actually get to work right and always causes you to scroll up or down when you go to click it. I like Logitech mice. Anyway, with that little aside, this right here is the first demonstration. Now, to show off, that doesn't actually show it there, but the demonstrations for, like, this is how it's actually written in the book, right? So, I'm not kidding whenever I say that is how it is written in the book. If you look in the book, that is how you're going to, I mean, the one actually is like over here, but other than that, I reproduced it as faithfully as I could for this graph. And I try to reproduce it as faithfully as I can for every graph that I do. Now the thing is that I don't add the QED, which this is what the QED for these look like. This is just that, right? So the QED, this 2, meaning this section, and 301 is the what I call like a justification for P and Q implies P. I also forgot the extra dot here. I am stupid. Imagine that there's a dot here, okay? So, this is what this is showing off. Now, on the left and the right are two different versions of how I group stuff. As I explained down here, if you want to pause the video, this is an alternate, this is where I'm experimenting with an alternative grouping method for grouping these together, and we're not going to necessarily go into the alternative grouping method stuff. What you need to get is that this is demonstration 1. And what's going on here is, as you can see here in demonstration 1, it says star 202, Q over P, P over Q. Now let's go look at star 202. We actually have it here. This is star 202. Q implies P implies Q. Now, if you look over here, the demonstration, like demonstration 1 or 202, is add, not P over P. Now, if you go look at add is Q implies P over Q. So let's copy this, paste it into our workspace. Add, no pun intended or even avoidable, I think. This. Right? So you can see here that this is add. So Q implies not P or Q. You get what that means now? That, like, not P in place of P in the same structure. This is morphological. Trying to... Here, let's get fancy. This is morphological. Okay? Meaning this form is being used here. So Q implies not P or Q. Now, what is the significance of this? Well, the text of add is let me look. Let me put on my fancy voice. I'm kidding. I'm not going to talk like that for this. The text of add, aka 1 point this principle states if Q is true, then P or Q is true. Thus, e.g., meaning example given, if Q is today is Wednesday and P is today is Tuesday, the principle wrong principle. Principle states if today is Wednesday, then today is either Tuesday or Wednesday. It is called the principle of addition because it states that if a proposition is true, any alternative may be added without making it false. The principle will be referred to as add. Okay? Now, we've already covered this with the concept overview we did of the logical disjunction or logical sum versus the concept of the logical conjunction, aka the logical product. This is a This is a rendering of that in formal propositional logic, and then re-rendered to my graphing system. Now, what this means is, right, that if you can add any alternative, as in literally any alternative, without making the proposition false, then obviously not P is also valid. If you're paying attention, this justifies logically not P yeah, or Q. My ear. As seen above, then you have Q implies not P or Q. If you take add and replace P with not P. Which again is valid because any alternative is valid in a disjunction. Get it? There's no reason that adding not P somehow makes add invalid. Okay? If you're not getting it, don't worry, I didn't either at first. And my ear's itchy, hold on. I'm setting down the headset. Legally obligated to tell you not use Q-tips. Understanding logic at all not suddenly make you smart. Understands logic. Alright? Understanding things doesn't make you smarter. I still put Q-tips in my ears. I'm clearly not getting smarter by reading Principia Mathematica. The reason you should read it is, I mean, the reasons are many and varied, and I'm not going to get into them here. It's just I will reiterate, if this interests you at all, read it. Okay? So the idea here is, alright, that's the wrong one. The justification of this is in the demonstration. So if we flip forward to 202, right, Q implies P implies Q. Now, obviously, if that is valid, as it says here, this is valid. Okay, let me undo that. My freaking mouse. Okay, and what I mean by that is, if this is valid, right, and it is, then what's actually being shown here, right, is Q implies P implies Q. You get it? Does that make sense? And this by itself is true. I mean, again, the statement, if today is Wednesday, then today is either Tuesday or Wednesday, is true. You can add an additional without making the statement false, right? Because if one part of it is true, then the statement is true. If today is Wednesday, then today is indeed either Tuesday or Wednesday. It might sound ridiculous, and Alfred North Whitehead and Bertrand Russell have moments in the book where they straight up say that. Like, there's moments where they straight up go in the first 100 pages. Like, sometimes we're going to say some stuff that sounds a little silly. Because you kind of have to whenever you're dealing with the most basic components of logic, right? Of propositional logic. So, to clarify again, Q implies P or Q. Meaning, if Q is true, then P or Q is true. Which is true. If, again, just reread this for a minute. So if this is a true statement, then you can add, right? Okay, so if Q is true, then that means that P or Q is true. Then, if Q implies that not P or Q is true, like if Q is true, then not P or Q is true, then that's the same, to continue the metaphor, as going, okay, if today is Wednesday, then it is either not Tuesday or Wednesday. Right? So, if today is Wednesday, and it is either not Tuesday or Wednesday, you get the idea? Like, in this instance, Q is just independently true. Sort of. Kind of. Right? That's kind of the difficult thing about what we're going over here, is that whenever you try to add, like, specifics onto it, it becomes a little bit different. Right? But remember the truth table that we had earlier, that P can be true, and Q can be true, and that'll be true. But if I say, so let's continue that metaphor then. If Q is today is Wednesday, and then P is today is Tuesday. Or rather, if P is today is not Tuesday. right? So if, again, in this, right, either, though I know that I'm getting this a little bit confusing, because the metaphor or whatever, the example given is that today is either Tuesday or Wednesday, implying that it is Tuesday, right? So if we're going to say that not P is today is not Tuesday, right? Then what we're saying is that if P equals today is Tuesday and not P equals today is not Tuesday and Q equals today is Wednesday, then if today is Wednesday, I'm going to stop capitalizing that because it's a pain. If today is Wednesday, then not P or Q is true. If today is not Tuesday, then not P or Q is true. If today is Tuesday and it is not Wednesday, then it is false. If today is Tuesday and it is Wednesday, then it is still true because the proposition was explicitly it is either today, or rather, it is either not Tuesday or Wednesday. And even though it would be nonsensical for it to both be Tuesday and Wednesday in this context, or rather with no further context, if it is Tuesday and Wednesday, then it is in fact meeting the necessary requirement for the proposition it is either not Tuesday or Wednesday to be true because it is because it has the property of being Wednesday. Right? The point being is that you're not looking at whether or not it is sensical for it to both be Tuesday and Wednesday. The satisfaction of the proposition is not predicated on metalogical sense making regarding realistic context. And besides, you could look at like some kind of context in which today might have a greater, more metaphorical meaning or whatever. The point being, thusly, that if it is Tuesday and Wednesday, then it is still Wednesday, right? Do you get the idea? And again, I know that that's a little nonsensical, but let's keep that up again. Because not P or Q is P implies Q. Now 101, again, right? And that itself deserves a look. So this right here is by 1, like this is 1, right? So if we look up here, in the demonstration for 202, this is P implies Q. That's 202. Now, rather, it's Q implies P implies Q. Now, demonstration 1 is, I actually think I did this wrong, because this says 1, and this is actually 1 right here. I should probably go redo that. Let me look at 202. Yeah, I did that wrong. This is the QED right here. This is actually the QED. I need to go redo this graph. It wouldn't be that difficult. I just need to like move the line up. So, but the point is that I'm glad I caught that. But yeah, this is one of the earliest graphs, so it's okay that I kind of had a bit of a mess up on that. But the point is that this is the QED, this is 1. So what this right here means, so kind of like how this is by add replacing not P over P, you get Q implies not P or Q, which by that and 101, which 101 is P implies Q is identical to not P or Q. By that and 1, you get Q implies P implies Q, right? Now that is just what's used here to then go, okay, in the demonstration 1 for this, you then have to kind of move all of this over and up a bit, over here, and to not cut off our mascot. Well, I don't know how you feel about it, but I consider it my mascot. The mascot, whatever. Let's fill that in real quick. So if you move this over here, and look at these two, right? So then you swap Q for P and P for Q, right? So instead of Q implies P implies Q, you get instead of Q implies P implies Q, you get P. I'm sorry, I can't talk. There's too many Q's and P's going on. Instead of Q implies P implies Q, you get P implies Q implies P, right? With the justification being 202, which is Q implies P implies Q, and the justification for that being add with not P replaced for P, which the justification for that is the very understanding of what makes add like cogent and logical. And then from that, you get, Q implies P implies Q, which, okay, so that's the justification for P and Q implies P. That's the first step of the demonstrative justification for why P and Q implies P is sensical. Now then we get into the next part, which is 1 and 101, right? Which implies the whole thing. So note that here, 1 and 101 comes before the starting assertion. The rest of the stuff here is under the purview of this assertion, like this initial assertion. This right here is in my graphing system, I use the therefore symbol because of what this actually entails. I'll explain that in a second. So for this entire sequence, the first thing here, right? So this means the first demonstration, and 101 justifies all of this. Now, why would that be? Well, if you have P implies Q implies P, then that is, right, not P or not Q or P. Right? Because that would mean that P implies, right? Oh, I forgot a thing here. Yeah, I'll fix that in a second. Hold on. Yeah, actually, that's the wrong thing. Crud. What I need to put there is, I'm glad I still have these. This. Yeah, I'm dim. That should not be that. You can tell that I made these kind of early in the morning, huh? Yeah, I was gonna say, I bet I did the same thing here like a lummox, and I did. Just bear with me, I know it may not be the most exciting thing to watch, but we'll be getting back into the demonstration shortly. No, actually, I'm an idiot. That made sense on that side. That's why that happened. Okay. Yeah, you can tell I'm just a little bit fried from doing all this talking. It's a little bit more exhausting from talking than you might think. It's correct on that side and not correct on this side because of how the nesting notation works anyway. The point is that, so if not P or Q, right, is implication, and not Q or P is Q implies P, right? Then if P implies not Q or P, okay, then that would mean that not P or not Q or P. Because the relationship there is that Q implies P means that Q is, again, what? Making that disjunction, like it's leaving no choice but for P to be true. You get, like, the commonality here is a disjunctive I'm just going to call it a disjunctive, like, negation component, right? So not Q or P. If Q is true, then P is true, right? Because otherwise, this disjunction would be false, as we covered earlier. Now, what that means is that up here, if this is P, if not P is false, which would mean P is true, because P is not P, then P implies Q implies P. You get the idea? Now, we go into the next one, right, which is 231. Now, what this is a conjunction. And the way to explain this, what this means is this. So the single dot right here means that this is not P or Q as a single unit. So this as a single unit, this as a single unit with this in between them. That's why I have that giant notepad thing in the background, by the way. Is in case exactly that happened. That's called forward thinking. Anyway. So the two dots, or the colon, means that everything between this and this is in a parenthetical, right? Now the thing is that it also means that this is a conjunctive. So this can be read as 231 and this, right? Meaning the whole thing, not P or not Q or P, plus 231, or not plus, but and 231. Therefore, you get not P or not Q or P. Now, why does that make sense? Well, let's look at 231. 231 is P or Q or R implies P or Q or R. Now, if I want to go into Principia Mathematica itself, something that will be relevant is the text, and we'll get to that. The text under 231 says, this proposition and 232 together constitute the associative law for logical addition of propositions. In the proof, the following abbreviation, constantly used hereafter, will be employed when, etc., etc. But what they are talking about when they mention the associative law, if I flip to the very front of the book, the associative law is also stated as star 1.5. So again, this proposition and 232 together constitute the associative law for logical addition of propositions. Now, if we go to 1.5, we get this. Which is P or Q or R implies Q or P or R. And I should have already, prepared for this. I didn't because I didn't read ahead. This is the one thing that I forgot to actually prepare for, but it's fine. Again, you'll actually get to see me make the graph, right? Right here, hot and fresh. By the way, this is a different symbol in Principia Mathematica. Like, what looks like a backwards implication is actually a symbol in Principia Mathematica that won't be brought up until much later, thankfully. Oh, and I'm stupid because those are not actually implications in this. I just read the thing, and yeah, I'm a bit dumb. That's fine. Text 24. Here's a little bit of insight into the graphing process. So let's graph this out, what associative is, right? Now 231, again, is a form of this. Right? Yeah, that's like way too low. Also, I don't know what that is, but I don't like it. I don't know why I have fuzz on my disjunctions, but I don't like fuzzy disjunctions. If you or a loved one has fuzz on your disjunction, please seek immediate medical treatment. Anyway, fuzzy disjunctions aside, and let's put that in blue. Because that is a primitive proposition. That is essentially the bedrock that we are dealing with here. Okay? Primitive propositions are very important. They are effectively the bedrock, like I just said, of what we're dealing with here. All of it. Like, all of it, all of it. It is very important to recognize them as such. Now, let's wipe that and let's restore this. It's fine. It's fine. One man struggles with his brain disease. Anyway. This also doubles as a documentary on OCD, folks. Anyway. We'll get to why syllogism is in purple whenever it becomes relevant. So, as stated, 231 has as text, not Mayans, Aztecs. No, seriously though, it has as text, if I could enunciate properly. Like I said, this proposition and 232 together constitute the associative law of for logical addition of propositions, which is P or Q or R implies P or Q or R. Now, if we look at star 1.5, which is, as shown up here, P or Q or R, implies Q or P or R. The text for it is, this principle states if either P is true or Q or R is true, then either Q is true or P or R is true. It is a form of the associative law for logical addition and will be called the associative principle. It will be referred to as assoc, or as you can see, a soc. The proposition P or Q or R implies P or Q or R, which would be the natural form for the associative law, has less deductive power and is therefore not taken as a primitive proposition. What they're saying here, if you want the real extended understanding of it, is saying that today is Tuesday or today is Wednesday or Thursday is no different than saying today is Wednesday or today is Tuesday or Thursday. Right? Functionally, there's no difference between those two things. Now, right, there's no difference between, let me type it out because I know that just hearing it can be a little confusing. So, today is either Tuesday or today is either Wednesday or Thursday. Is no different than today is either Wednesday or today is either Tuesday or Thursday. In truth value. This is as covered with disjunctions, the concept of the logical sum, to do with how disjunctions work as propositions. You can add alternatives without affecting the truth value. Again, f plus t equals t. 0 plus 0 plus 1 equals 1. Okay? So we look at that, and that's how you get that kind of an idea of what's going on there, right? But if we're going to look at the actual justification for it in the demonstration, and we are, because this is actually what this is about, is drilling down back to bedrock on these. So the justification for 231, I'm just making sure that the first one is 230, like in what is 1, and I would like to believe that that is what it is. Yeah, okay. I'm just reading this to make sure that I've got it right. Okay. So justification 1 is, now this means this is the entire proposition. All of this is the proposition. Like you see over here how this, it's the same, it's literally the same idea as this, it's just way larger. Because whenever I did this, I was making them a lot wider for some reason, don't ask. But yes, this is the concept, right? So this is the same grouping method. This is all the same, right? Kind of like this is all the same demonstration, like this is all part of 1. Or rather, not part of 1. This is all part of 2, I misspoke. Like, all of this right here is 2. And thus that's represented here by this, and then this is all part of the same assertion. This is all the same assertion, and specifically, I messed this up. This should be up here. Again, that's another little nitpick I'm going to have to fix, but the idea is simple, that this is the first part of this assertion, that P or Q or R implies P or R or Q. But then that, by associative with R replacing Q and Q replacing R, so you swap those two. So this would be, here, let me, instead of doing that like a nitwit, like I did before, so by this, so 230 justifies this whole thing, right? Let's look at 230 then. 230 is P or Q or R implies P or R or Q. Now, it is justified by perm Q over P and R over Q. Now, let's look at that next. Actually, let's get rid of that. Move this in here. Now, what is perm? Let's go look at 1.4. It says P or Q implies Q or P. This principle states that P or Q implies Q or P. It states the permutative law for logical addition of propositions and will be called the principle of permutation. Will be referred to as perm. It's the same idea. It is Tuesday or Wednesday is the same as it is Wednesday or Tuesday. Right? So you take perm, you replace P with Q and Q with R, and you get Q or R implies R or Q, which is true. So then that, and again down here, the demonstration is then sum with Q or R over Q and R or Q over R. So let's look at sum, which I thought I had already graphed. I am behind. Wait, it should be up here, yeah? Ah, here it is, yes. I am just dim. Now, again, I think I already covered some, but let's be real with it. And just go ahead and read the text for 1.6. This is Q implies R, implies P or Q implies P or R, which the text under it says, this principle states, if Q implies R, then P or Q implies P or R. In other words, in an implication, an alternative may be added to both premise and conclusion without impairing the truth of the implication. The principle will be called the principle of summation and will be referred to as sum. Okay? So, with that, if you take perm Q over P and R over Q and sum Q or R over P and R or Q over R, you get this. Okay? So you get and see, that's how I did it in this section. Like, you could see that my notation has evolved somewhat and will probably continue to evolve a little bit, but I think I've finally nailed down how to do the therefore stuff. The point being that this plus sum with Q or R replacing Q and R or Q replacing R. You put those together and you get, so you put this together with this, get this, which is P or Q or R implies P or R or Q. Right? So you're taking the Q or R here, and you're so again, sum is Q implies R implies P or Q implies P or R. Now, the back half of this, and this is what the therefore takes some explaining, is that this is why I eventually changed this. So what's going on here is that you're looking at the consequent of this. So if you take sum and replace Q or R over Q, right? And R or Q over R. Now, R or Q over R, to make this, right, you're looking at what's called the consequent. This is the consequent. This is the antecedent. What is happening in this, whenever it does the therefore like that, you're basically slamming what's in this, right, into the antecedent. Like, that's what that means, is that, I mean, I think it's kind of obvious, right? Like, you look at this before I butchered it. The only way that those two things make sense is if you are looking at and using the antecedent. So what's going on here is that this is being put into the Q, and this is being put into the R, right? As antecedent and consequent being put into the antecedent and the consequent of the greater antecedent and of this larger proposition. So if that's a little confusing, what I'm saying is that if you take this, let me copy it again. Do I have it? Yes, I do. Thank goodness. What I'm saying is that if you take this, right, what's being done here is oh, let me do one better and explain it in a visual way. This is the antecedent of the larger thing, right? Like this would be the antecedent between these two, right? Now this is the antecedent between these two, right? So this right here is the consequent, right? Now this, within this nested proposition is also the consequent, right? You following me so far? So what you're looking at, and this right here, again, just to prove the point, right? I'm not sure if in a disjunction they're technically an antecedent, but like in an implication, this is definitely the antecedent, and this is definitely the consequent. I'm not so sure if I could call this an antecedent here, but you get the idea. Like in this implication, this whole thing is the antecedent. What is happening here is that this is being put into the antecedent here as the antecedent here, and this as the consequent. Let me find a better color for that. Like, yeah, there we go. And that as the consequent is being put into the consequent here, right? This is a form of substitution. So what yields from this is that you're putting, okay, the substitution here which we'll color purple, right? This is the substitution that is going into that antecedent, and we'll leave the consequent substitution as yellow, okay? So what's being done here is that they are being substituted again, right? Like you can look at them as being mushed into this structure, and then that is what is used to do the substitutions here, right? This is more important for actually being able to read Principia Mathematica cogently. This isn't like so much a logic thing, and it kind of is, but this gets more into my stuff, which is all about isomorphism, morphology, form behind content, like that kind of stuff. That's what I'm mostly interested in. So that it makes sense why I'm so persnickety, finicky, and like going into a ton of detail on this whenever it might seem a little granular and weird. But that's how you can look at what's going on here. So whenever it says, okay, right here, that this, Q or R implies R or Q, and sum Q or R over Q, R or Q over R, therefore, like what it's doing is Q or R is going into Q, R or Q is going into R. It's a direct how would you put it? Like, you can see how it's one-to-one. That the antecedent is going into the antecedent, right? The antecedent is going into the antecedent. The consequent is going into the consequent, right? And that makes this substitution into its own separate entity. Like, that's, again, it's the substitution game being played laterally, right? That's the justification game being played laterally here. So that's how you get the justification for 230, which is that this still makes sense. Like, this still holds. And it does. Like, P or Q or R implies P or R or Q because it is just as shown in sum, right? It's just another addition being added to both sides of the implication. It's no different. It's just that you're dealing with, you're mushing together basically sum and permutation exactly like it shows there. Now that's the justification, again, and for 230, which 230 is the justification for all of this, which is 231, to get back to it. The demonstration is 230 renders P or Q or R, right? So if you look at 230, P or R or Q, right? That's 230, P or Q or R, P or R or Q. And we just showed how that makes sense, right? There's nothing wrong with that. It makes sense by the logic of perm and sum. But we're looking at the same thing essentially just with the inverse, where instead of P or Q or R and P or R or Q, it's P or Q or R implies P or R or Q. It's P or Q or R implies P or Q or R. Right? That's what 231 is, which, if we follow it down, the whole thing is justified by 230. So we get down, and the first segment right here, this, of it, the second part, and this is a little different to describe, but basically what's going on in the notation to show it here is that it is written and then it has a conjunction followed by, and then it goes into, like before, the like I explained earlier, I do believe, like this, right, where it has a like I said, like it has a conjunction which follows into the next thing. Now the thing is, or like I explained here, right, like this is a conjunction and it means this and the next thing, therefore you get the thing resulting. Now the difference here is that this is the thing being used as a conjunctive, because this goes to this and no further. It does not include the antecedents. So the consequent of this, right? So the consequent here is being used with associative R over Q, Q over R. Now let's get up to associative, right? Let's go ahead and get that. Actually, I think we had that already, yeah. My brain's going a little bit because I've been at it for so long. Yeah, okay. You go ahead and copy this. So you got associative. And then this says, this P or R or Q plus associative, like that and associative, renders R or P or Q, right? Or rather implies. That and that applies, implies, rather, R or P or Q. Now the reason why this and that, like this used as a antecedent in conjunction literally with some, right? I'm a bit dim. Hold on. This used in conjunction with some. Right? Renders, like, through implication, this. Okay? So it says associative R or Q, R over Q and Q over R. This is associative, right? And then you get Q, instead of Q or P or R, you get R or P or Q. Now the reason why this plus associative implies, like P or R or Q, plus associative implies R or P or Q, is that if you look, right, P or Q or R, Q or P or R, P or R or Q, R or P or Q. You see the morphological reasoning here? The idea is the same between these two as what it is between the antecedent, like this used as an antecedent, using, like, in conjunction with some, no, associative, like this in conjunction with associative, renders through implication this as the consequent. Because if you apply blank or, like, blank 1 or blank 2 or blank 3 implies blank 2 or blank 1 or blank 3. Let me write that out. Because the idea here is blank 1 or blank 2 or blank 3 implies blank 2 or blank 1 or blank 3. This is a morphological schema, meaning it doesn't matter what is in blank 1. This is why if P is blank 1 and Q is blank 2 and R is blank 3, I should have just said if P is blank 1, Q is blank 2, and R is blank 3, it renders what it does. But if P is blank 1, R is blank 2, and Q is blank 3, then you get what is shown in the third grouping of 231. 231's demonstration 2. I think that's demonstration 2, right? No, it's demonstration 1. I'm stupid. So to put the point home, like to drive the point home really, 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 really surely, right? Again, this is more like understanding how to read Principia Mathematica, but it is also important in understanding why this stuff makes sense, right? So the thing is that maps directly, right, over to here. So this is the same thing. Okay? Like, this is the same morphology, meaning this is the same form. This is the same form of thing. Now, if you want to get real, what is happening here is, essentially, you can view this as a transformation done by taking this and going, if this is the antecedent, and we are looking at associative, I believe it's associative, right? Yeah. Then this is the, like, consequent. Like, this would be the consequent of this. So if we're going to take this as an antecedent, let me stop being dim. As difficult as that is to imagine. if we take this as an antecedent, what we've got here, if we use the morphology of... Okay, I need to... How about this? If we use this as an antecedent and follow the morphology of associative, we get this as a consequent. Okay? That's what that's actually doing there. It's like it's using this, filtering it through the morphology of associative, and you are rendering the consequent thusly. Okay? Through implication. Like, what does this imply? If you were going to use it as a consequent, like if you're going to use it as an antecedent and an implication, and your implication was filtered through the lens of associative, this would be the logical, like, next step according to that form, according to that schema, that concept. Again, if blank 1 or blank 2 or blank 3 implies blank 2 or blank 1 or blank 3, if you run P or R or Q through that schema, what you will get as a consequent is, in an implication, R or P or Q. That is why associative is being mentioned. This is another, again, lateral substitution, if you will, right? And the same thing is being played out here with perm with the previous. So if we take, if we take R or P or Q, and we look at perm, all right, let's copy this and paste it. That is perm, right? I got that correct? Okay. And we run that through perm. And we get an implication. Again, notice here, R is going over P. P or Q is going over Q. And why is that? Well, I'll explain it to you. What is being shown here? This right here goes over this. Okay? As the antecedent and the consequent. So, naturally, if this is being ran through this schema, then what you get morphologically is Q, right, or P as the implication. You get the idea now? I'm not like saying this in that way because I'm... by the way, if I ever sound like I'm condescending, understand I talk like this because this is how I remind myself how this stuff works. Like, this stuff took me way too long to understand, and I am trying my best to help you understand it. That is why I talk like that. I do not think myself intellectually superior to anybody. Like, I talk like that because that is how I learned it. That is how I went, I understand what's going on here. This stuff blew my mind. That this is a morphological transformation. This is this being ran through a filter. You are literally like coffee in a coffee machine, running your coffee beans through the filter of insert whatever thingy here. And this is how you get that out of there. Okay? Again, this is very important to being able to understand Principia Mathematica, and it is important that you are able to understand that book if you want to read it, and you should read that book, so I want you to understand it. Capiche? We good? Because again, this took me a lot to like look at and go, oh, that's what's being done there. Yeah? So that's why this makes sense. Okay? This all holds up all the way down to bedrock. So that's the justification for 231, because all of that holds up. Get it? Now, 231 itself was the justification for this, which, again, if you look at this, so not P or not Q or P, which as we discussed, like 1 here makes sense. We covered why that makes sense. So 202, right? Not Q over P, or rather Q over P, P over Q, right? 202. You're just flipping Q and P to make the first demonstration of 326. And that makes sense because, like, again, 1, like all of this, P implies Q implies P, and 101, which states that P implies Q is identical to not Q or P, right? Again, that filtering, like you run those through and you get not P or not Q or not P, or rather not Q or P, excuse me. You get not P or not Q or P. Now that plus this, right? This and 231, which we just covered, why that works. So do you understand how that and 231 works? So just like before, we take this, okay, and we look at what 231 is. This is 231. I can shrinkify this. It's not going to hurt anything. But do you notice what? So we get not P or not Q or P from P, well, from 202 with Q over P and P over Q, right? Put through 101. And then this plus 231 gets you this, right? Therefore, this is valid, right? Now, why is that? You can understand, right? Like we've gone over why we get P or Q or R from R or P or Q. And 231 itself is P or Q or R implies P or Q or R. We've followed the justification chain all the way up. So if you go through this, what it's saying is that by 231, from this is valid, right? So you're running not P or not Q or P through 231, and by 231's established justification, not P or not Q or P is valid, right? So, and it is. Right? Because if you look at perm, again, I mean, we've discussed it, but just think back to how perm relates to this, right? So through that, you validate the second step within the second demonstration. That would be this step right here. Validate that. And then 253. It's that same substitution as before. By 253, not P or not Q over P and P over Q, you get not P or not Q implies P for the end of 2. That's this right here, right? Now let's take a look at 253. Now what is 253? Now this is going to be a bit of a doozy, right? 253 is P or Q implies not P implies Q. Now that on its face is kind of sensical, right? If not P or Q means P implies Q, then it makes sense that P or Q would imply not P implies Q, right? Like that makes sense, but the thing you got to remember about Principia Mathematica is they are making sure that every single link in the freaking chain is justified. I mean, imagine you were building a brick wall and you left out a brick because you went, all the other bricks around it are already mortared. That's stupid. You would be fired. That is not what these men were doing. These men were laying a brick wall of logic, a mile high, and they needed to mortar every single brick with no excuses and no missed steps, and that's what they did. So even though you can easily infer, if not P or Q is, like, if you can infer informally that not P or Q is P implies Q, and then from that, like, if you can infer from that P or Q, okay, let me start over. If you can infer from not P or Q is P implies Q, that the inverse is true, that P or Q implies that not P implies Q. Even if you can infer that informally, that does not matter. You need to prove it. That's what these men felt, and they were right, because again, they were building a system in which they justified all of this stuff. They didn't leave out a single brick just because, guys, you can get it, right? Like, no. So, we go to 253. And the thing is, 253 is kind of unassuming compared to some of the other stuff in the book, but it has 212 and 238. By 212 and 238, you get P or Q implies not P or Q. Okay. Right? Now you might be like, okay, hold on. Not P or Q, I meant. Yeah. So P or Q implies not P or Q. It's supposed to be, yeah, not P or Q. Huh. The thing that's interesting about that is that's a bit of a brain breaker for me, but we can get into that later, right? And I mean, that's true, because P or Q implies not P or Q, because, not P is just P. But the reason why that's a brain breaker for me is because of what that insinuates, that it's not P, right? Just like, again, not P or Q is P implies Q. So naturally, not P or Q implies that not P implies Q. Do you get the idea? But to go forward, like that's why that broke my brain for a split second. But let's go into 212 over here, which 212 is 211 with not P over P. 212 is just P implies not P. Now, did I actually go back and get... I thought I did, and if I didn't, I promise you I will just type it out, tickety type it out right here. I don't think I did for some reason. I thought I did. Okay. 211 is... P or not P. Oh, no, I have it right here. You can tell I am sleepy because, man, I completely missed that. Wow. Wow, I'm sorry, folks. I am, like, out of it today. But, yes, you can see that 212 is P implies not P. Okay? And that is demonstration 1 right there. Is it is 211 with not P over P. And 211 is P or not P, right? And as you can see, it's perm, not P over P, P over Q. Now, we've looked at perm enough times, but, you know, it's worth noting again that you're putting not P over P and P over Q. Now, what we've covered already is important, but it's worth saying again that with addition, the thing that is most important about addition, that cannot be stressed enough, is that if a proposition is true, any alternative may be added without making it false. Right? So if a proposition is true, you can just slap a disjunction on it. There's no problem with that. You can just slap a disjunction on a proposition if it's true. There's no change to the truth value. Now, the reason why that's important is because that implies that you can just do this, right? Again, that you can just swap P for not P and Q for P, right? If the proposition is true, you can add a disjunction. If P is true, you can add not P. If not P is true, you can add P. Just don't add P to your pool and you'll be fine. It'll end up as blue as this diagram over here. Dumb jokes aside, you get the idea, right? This is just perm, again, demonstrating that it's the same idea. And it's true. Because again, perm is that, you know, it is Tuesday or Wednesday is no different than it is Wednesday or Tuesday. Tuesday or Wednesday, Wednesday or Tuesday. It is not Wednesday or Wednesday. It is Wednesday or not Wednesday. Same idea, right? Like this implies that. Now, that's 211, which is P or not P. Right? Simple. And again, this is the law of the excluded middle. Apparently. It literally says that in the book. P or not P. I don't know what else to say. Anyway, if you add not P over P, right, for 211, how do you get not P or not P? right? So this is P implies not P. So how do you get P or not P or not P, right? Oh, this is supposed to be P and no, that's this one right here. Yeah, okay. This is supposed to be P implies not P. So you'd be correct in wondering again, how do you get not P or not P from that? Well, actually looking at the book, right? P, right? If this is not P, and you put not P here, right? What then do you get if you add P? You kind of have to work backwards a bit. Because, again, what is P implies not P? Right? Like, if you add not P here, what is the relationship between P and not P not P and not P here? Well, the relationship is that P, right, has its negation on the other side. If you add not P for P, you get its negation on the other side. Now, the negation of not P is not P. Now, if not P or Q, and this is like a bit of a brain buster, but so P, well, let me copy it again, because this is another morphology thing, right? The reason why I'm taking it so slow is because it takes it takes someone like me who is very into the morphology of this stuff a minute to kind of process this. Because I had forgotten this. I was actually asking that stalling for time. I'm not going to kid you. But like I get it now. This is looked at by its negation, right? So antecedent to keep with the coloring scheme from earlier, ketchup and mustard, right? Let's go for a different color. Now, this is going to be a lesson, if you will, a demonstration in a kind of different, sort of, maybe weird kind of morphology thing. So we've got our operator, our antecedent and consequent. So the antecedent here, I meant to copy that. So the antecedent is obviously P in the first instance and not P in the second. The consequent is not P here, and then not P, and the operator is the OR operator. Now, what we're actually looking at is the relation. Now, to visualize this, okay, and the relation between the two is, as before, blank 1 is blank, and blank 2 is not blank 1. Okay? So this holds, this relation, across these, how would you want to put it, configurations? Because again, what is happening is you are mushing not P into P, and then the relation is still preserved in that morphology, right? It's saying here 211 with not P over P yields not P or not P, because blank 1 is blank and blank 2, right? And if you want to be really like particular about it, red is red, and yellow is not red. Get the idea? So if blank 1 is red, then blank 1 is blank 1, right? Is blank 1 is blank. Blank 2 is not blank 1. Whatever blank 1 is, it is not blank 1. That is the relationship here that is preserved. Okay? It's a bit of a mind bender, and it just head kicked me again. It took me a second looking at that because I completely blanked. As you can tell, I'm still kind of out of it. I've been going at this for a minute now. But like, Yes, that, and by the way, I didn't write a script for this, not that it wasn't obvious. But yes, so that's how this is justified, is that P or not P, right? 211 not P over P. Well, not P or not P, because again, of the relation preserved between the two. And because not P or not P, right? If not Q, or rather not P or Q is identical to P implies Q, then not P. Oh, I'm a bit out of it, folks. Sorry. Not P or Q is identical to P implies Q, then not P or not P is identical to P implies not P. And again, it's because of this preserved morphology, right, that makes sense. The morphology is if not P or Q, so yeah, you get the idea, right? Like, again, this, I say it like that because this takes me considerable effort to, like, you know, like, I'm astounded by it too. That's the other reason, is that I find it profound. I find it actually profound. I find it fascinating and profound. So that's part of it. That's one half of this, right? That's one half of the justification for 253, which is part of the final justification for the second part. You get the idea. Okay, so what's the second half of this? Of the justification for 253. 238. Well, let's look at 238. 238 is Q or R implies Q or P implies R or P, which is SIL plus SIL and perm and sum. Now, if we look here, this is directly from the book. The proofs of 237 and 238 are exactly analogous to that of 236. Okay, so let's look at 236. Q implies R implies P or Q implies R or P. Now, by now, you will understand how this works, but again, let's read through it. So perm, if we look at this, justifies the entire thing, the entire string for one, but look at that nightmare, huh? Perm, P or R, implies R or P. Sure, right? Now, SIL with P or Q over P, P or R over Q. P or Q over P, P or R over Q, R or P over R. What a nightmare, right? Now, the thing is, again, this is both of these, not just the second grouping. This is both of these because of the colon on either side, the two dots on either side, right? This groups this whole thing. So this whole thing and SIL, which is syllogism. Now, the thing about syllogism is, and the reason why it's in purple, is because syllogism is very special. It is basically, it is not a primitive proposition, but it is like just one step up above that. Okay? And syllogism is Q implies R implies P implies Q implies P implies R, which is, I think, very beautiful and is a very old thing. But if you look at it, it says sum, not P over P. Now, what's sum? Q implies R implies P or Q or implies P or R. And you legit just replace P with not P, and you get P implies Q implies P implies R. Legit, right? And again, the reason that that's legal is because of add. excuse me, let me have my voice not crack, is because of add. Because you can add any, if a proposition is true, you can add any disjunction, right? Like, there's no reason that you can't add not P instead of P. If Q is true, there's no reason that you can't add not P. If R is true, there's no reason that you can't add not P, right? And again, if R is true, there's no reason why you cannot add not Q, which would be Q implies R. Okay? So then you take sum and you put not P, again, instead of P or Q and P or R, right? And this is literally, by the way, not Q or R implies, you get the idea. You get the idea. So we get into the syllogism, which is Q implies R implies P implies Q implies P implies R, which is sensical, right? So let's say Q equals trash day, and R equals taking the trash out, and P implies Thursday, because I'm tired of typing Wednesday. Wednesday's perfect because it's the middle of the week, but like I'm tired of typing Wednesday. It's too much. So if it being trash day makes it the day to take the trash out, then if Thursday is trash day, then Thursday is the day to take the trash out. Right? Okay. That's the basic way to understand Q implies R implies P implies Q implies P implies R. Because if P implies Q, then Q and Q implies R, then P implies R. You don't have to like do the whole chain. It just makes sense. It just works. You know, cue the gif of the guy slapping flex tape on the thing, right? Like it just works. Yeah. Okay. So, syllogism though, if we look at it, let's bring it down here. Let's bring it on down. So, P or R implies R or P. You notice what's being done here? P or R is going into Q. R or P is going into R. Now, the curious thing is P or Q is going into P. Now, why is that? Well, let's look at it, right? And again, that's why this is like presented as the antecedent almost. Is because what a nightmare that is, right? Because again, this is these two, like this implies this, implies this, implies this. But if you think about how syllogism works, right? This is P or R, or P or R implies R or P. Now again, as before, it cannot be overstated that what's going on here is this. right? That is being fed as the antecedent into the antecedent, and this is being fed as the consequent into the consequent. Okay? Morphologically, this is what is going on here. Right? Now, why then P or Q over P? Well, let's look at what P is. Right? What is going on in syllogism? Right? In this, P first shows up in the antecedent. Like P shows up in the antecedent as an antecedent within an antecedent, right? Like it's within the consequent, but of the primary. Let's separate this into tiers, right? So you have the first highest level antecedent consequent relationship. Let's make this very simple and just highlight these, right? This is the first level of the antecedent and the consequent, or the highest level, the uppermost, largest level, if you will. And then we have, within this, and within this, the second layer of the antecedent and consequent relationships. Okay? And then within that, we have the next layer, even thinner, of antecedent and consequent relationships. I promise I'm getting to a point here. Okay? So we have 1, 2, 3 layers of antecedent and consequent nested within one another. P first appears within the third nested layer. It only appears even in the third nested layer. Q and R appear in the second nested layer and are a single unit within the larger antecedent, largest even, antecedent consequent relationship. And they reappear nested within the second layer in the third layer independently of one another on separate sides of the second layer's antecedent and consequent relationship. Now then, from whence P and Y is it P or Q over P, right? Whenever you've got P or R going into Q and R or P going into R. Because again, it is P or Q that is going over P. Let's take a look at this relationship and see if we can figure out what's going on here. This is P or R, right, for Q, and R or P for R. What? Let me put it another way. So again, this is P or Q implies R or P, right? P or Q implies P or R. What's going on here is, if I can get my brain to articulate this properly, as fried as I am at the moment, is that P or R implies R or P, right? P or R implies R or P. Now, much like Q implies R implies, right? Now, if P or Q implies P or R, implies P or Q implies R or P, what is actually being stated here? This is just the third wheel again, right? So Q implies R implies P implies Q implies P implies R. What this is another wheel, right? Like another thing being added. It's how you get, right? It's how you get the whole, like, why not add instead, like, Q or R or whatever. It's just simply an added thing. Just like this, you know, this could be said that it's like a third wheel because you're adding P into the mix, which you shouldn't do. Never add P into the mix. But the idea is that, yeah, you're going with Q implies R implies P implies Q implies P implies R. The Q is more or less just coming in as an addition to it, right? Now you take that and you go into sum, right? And it shows here that what you get is P or Q implies P or R implies P or Q implies R or P. And then from that you get Q implies R with sum, right? And we've seen enough of sum, right? Which is, we've seen a bit of sum anyway. Q implies R implies P or Q implies P or R. Now that's kind of the other thing, is that if you want to look at sum, P or Q, right? But if you were just trying to infer it from this, it makes sense as just an additive. But if you put that through sum, you do indeed get, right? Q implies R implies P or Q implies P or R. Which again, the entire point of this whole exercise to go back to 237, 238 even, is that they're analogous to that of 236, and the point of 236, if you want to say it has a point, right? Is to prove Q implies R implies P or Q implies R or P. And what that's actually saying is that, again, it's just a different way of showing that P or Q implies, I believe it's, hold on, let me look at that again. It's Q implies R implies P or Q implies R or P, which is, I mashed these together in my head anyway, but okay. Q implies R implies P or Q implies R or P. So that's still Q implies R with an extra P added, right? Like with, yeah, that's sum, basically. Just with, what's the one that I'm looking for? With perm. It's sum plus perm, essentially, right? Where you can flip P or R to be R or P. That's legit it. And you could tell that just if you just look at it, right? But they have to go through all of the justification to make it make sense. Because look. It's just that, right? But you can't just go, it's just that. You have to show the justification all the way down for it. So anyway, that is the other half of this, the 212 and 238. For the demonstration of 253, show that P or Q implies not P implies Q, through the demonstration that P or Q implies not P or Q, through 212 and 238. Again. How is that? Well, 238, Q or R implies Q or P implies R or P. And then you have 212, which is P implies not P. Which you can mash them together. Right? By the way, the reason why this is here, if this will stop, is because it actually shows that on, as you can see right here, that it says it is sil and perm and sum mashed together. It is syllogism and permutation and summation mashed together. That is literally what 237 and 238 are. Like 236, 237, and 238 are literally just syllogism and permutation and summation just smashed together. So by that, like, that mashup, that mixtape, if you will, you can get P or Q implies not P or Q. Because P implies not P, right? And if P implies not P, right? Then P or Q implies not P or Q is cogent, which would mean P or Q implies not P implies Q. Because not P or Q would result in not P implies Q, and not P is not P. Right? And that was all, right? That was all of that. All of that is to justify this, which is not P or not Q implies P. Which then, because it is not P or not Q, it says 2 and 301 results in P and Q implies P as the QED. P and Q implies P. Which, let's look at 301. 301 is P and Q is identical to not P or not Q. That's the entire justification chain. For 326, just to prove that P and Q implies P. Because P and Q is not P or not Q. And not P or not Q. Get the idea, I think. Right? Because again, we go up here, and it's P or Q implies P. Then through that, at 101, we've got not P or not Q or P. And that can logically be, that implies not P or not Q or P. I think that last one, let me check. Yeah. Because again, not P or not Q or P, so not P or not Q implies P, and not P or not Q is just P and Q by 301, which defines P and Q as not P or not Q. So if not P or not Q implies P, then P and Q implies P. Get the idea? Yeah. Okay, this has been an absolutely massively long journey, and my brain is fried because I have been talking for way too long and I have been doing way too much explaining. So if I messed up too egregiously in any one part, please don't sue me. Thank you for watching this extra special yeah, if I cut there, it's because I hit the Windows key, and Windows being Windows, it just popped right up. But anyway, this extra special not G leader, this extra special episode of Principia Principia Mathematica. See ya. I've got editing to do. Till next time.